This is my second video on exponential growth and decay. If you missed the first one, you missed some basics. You may want to go back and do this, or go back and watch through that. Sorry. I'm going to roll through 4 examples about exponential growth and decay. Hopefully that will be useful to you. All right, bacteria in a certain culture increase at a rate proportional to the number present. Let's say Y is the number of bacteria, which means now we can go back and rewrite this. Bacteria increase, or the growth rate, the rate of change of the bacteria over time, is proportional to the number of bacteria present. So we start off with the rate of change equal to some constant times the number present. Let's see. So the number of bacteria doubles in 3 hours. In how many hours will the number of bacteria triple? Well, that's actually not that hard of a problem, but I already know the answer. The number of bacteria triple somewhere greater than 2 and less than 4 hours. Well, why would that be? Well, the bacteria double in 2 hours, double again in another 2 hours, at which point you have 4 times as many bacteria, so that's going to happen halfway. Oh, I'm sorry, in between. Probably not halfway in between. That seems a little. This is a calculus problem, which means we're expected to solve a differential equation. dy over y is equal to k times dt. Always separate variables, and I am, as always, a fan of doing that twice, since we're preparing to take that AP calculus test. Normally we'd write natural log of the absolute value of y, but the number of bacteria is never going to be negative, so I feel confident rearranging without absolute value. We're going to exponentiate, and what's that going to look like? Let's do that in another color since we're starting a new one. E to the power natural log of y is equal to e to the kt plus c, or y is equal to e to the c, e to the kt. This is always going to be the case, but just a reminder, let's let time equal 0 and y equal the initial amount. So we're going to have the initial amount is e to the c, e to the k times 0, or the initial amount is e to the c. Almost there. So our new equation, the total amount of bacteria is going to be the initial amount of bacteria, e to the kt. So it doesn't seem like we have enough information to go on, but we do. I'm realizing earlier I told you something wrong. I said between 2 and 4 hours. It should have been between 3 and 6 hours. I'm sure some of you are smarter than me and already figured that out. So I need a new color. How about green? Nope, we already did green. Orange. The number of bacteria doubles in 3 hours, so that means I could say, well, my initial amount, that's easy. E to the power of k times 3 is easy. How much bacteria are we going to have left over? Or at the end of that 3 hours? Well, that's easy. I don't know how much I started with, but I do know I'm going to have 3 times whatever that number is. So I can just say 3 times the initial amount. Oh, that's actually pretty easy. So divide both sides by y sub 0. 3 is equal to e to the 3k. Take the natural log of both sides. And k is equal to the natural log of 3. And then imagine the 3 here, but divide both sides by 3. So over 3. So now we have our k value, and the amount of bacteria is the initial amount of bacteria, e to the natural log of 3 over 3, times the time. And let y equal I must be dumb at the end of the day. I'm just realizing I already did tripling, but in the wrong amount of time. Doubles in 3 hours. Let me go back. doubles in 3 hours, I would have had a 2 here. Where are we? A 2 here, which means that would be a 2. The 2 would be there, and natural log of 2 over 3. If you got that ahead of time, like I said, I'm a high school teacher. I haven't made much with my life, so I'm sure you're smarter than me. Okay, so we're going to say let y equal 3 times the initial amount. So 3 times the initial amount is the initial amount, e to the natural log of 2 over 3 times time. And we're going to take natural log of both sides and divide by 3 natural log of 2, or natural log of 2 over 3. And so that would be the time. All right, I'm assuming you're capable of punching that into a calculator, and hopefully you get something between 3 and 6 hours. That was a pretty terrible example on my part. I think it's probably good to leave things in there. Hey, not all this stuff has to be perfect the first time. Puppy weighs 2 pounds at birth and 3.5 pounds 2 months later. Okay, I've never had tiny puppies, I'll believe that. If the weight of the puppy during the first 6 months is increasing at a rate proportional to its weight, let W be the weight of the puppy. Okay, so how much will the puppy weigh when it is 3 months old? So we're going to say that's time equals 3, time equals 2. And when the puppy's 2 pounds, that's time equals 0. So the weight of the puppy is increasing. So that's the rate of change of the weight. I assume that changes over time, proportional to the current weight. Yes, that makes sense. With a bigger puppy can eat more food, would gain more weight more quickly. Okay, that makes sense. Maybe not forever. Okay. The calculus is going to be separating variables, so 1 over w dw is equal to k dt. You know what I'm going to do? Rewrite the integrals on a separate line. Natural log of w, the weight of the puppy won't be negative. We don't need absolute value. Exponentiate both sides. And w is equal to e to the c, e to the kt. Let's use that initial condition. Time is 0, and the puppy starts off weighing 2 pounds. So let's see. Time equals 0, weight equals 2, means 2 is w, e to the c for now is e to the c, but we know what e to the c is going to be, and e to the k times 0 is just 1. So that means we can write 2 e to the kt. Now we use our intermediate piece, 3.5 pounds 2 months later. Let's use a different color. So time equals 2, weight equals 3.5. And what is that? 7 over 2, so 7 over 4. Inside the natural log, divided by 2 is equal to k. So the weight is going to be 2e to the natural log of 7/4 over 2 times k. How much will the puppy weigh when it is 3 months old? So that's time equals 3. Super ugly. Let me try that again. Natural log of 7/4 over 2 times the, I write k? should be a blue T. This time should be 3. And again, punch that in. Write out your answer. I'm not going to waste time. I know you folks know how to use your calculators. I hope this doesn't hit too close to home, but it's at least relevant. Obviously, we're not talking about, this is recorded in 2020. We're not talking about COVID, but it does make sense, to me at least, that the growth of the number of infected people is proportional to the number of people that are infected. If only one person is infected, that person is going to interact with not very many people. So that more people don't get infected very quickly. But if you have a bunch of people infected, then each of those people interacts and a lot more people get infected more quickly. So let's see. The number of people that are infected at any time increases at a rate proportional to the number of people. I assume you're getting bored with this by now because it's always the same, and you are right. So what are we going to call the number of people that are infected? So the number of people that are infected at any time increases at a rate, so I assume increases over time. The rate of change of the number of people infected increases at a rate proportional to the number of people infected. And you know where this is going. We are given an initial condition, an intermediate condition, and, well, some question about what's going on at some later time. Separate variables. Integrate both sides. We don't need absolute value on the population. Population is always positive. So the population is e to the c, e to the kt. Change colors, time equals 0, and there are 1,000 people infected. Well, I guess time equals 0 doesn't refer to the beginning. Time equals 0, as you can see, is when the epidemic is discovered. And so, e to the c is 1,000. The population of people infected is e to the kt times 1,000. Let's use our intermediate data point. 1,200 people are infected. 7 days later. And what is that going to be? 6/5. Inside the natural log, divided by 7, is that k value. I'm hoping you're okay with me moving a little more quickly. And so how many people are infected 12 days later? Hey, that's the easy version. I need p equals. Now, it actually is fairly important. It says 12 days after the epidemic is first discovered. You might get a question like in 12 additional days. If this had said, hey, in 12 additional days, we would have had t equals 19. But 12 refers, in this case, way back to the beginning. So the number of people infected is 1,000 e to the power. Natural log of 6/5 over 7 times, what is that, 12. Again, calculator time. I hope that was enough for you. I also assume you kind of put this on fast forward speed at one point or another.